Okay. So here's an explicit formula for a. So this is the Weierstrass function, and it was kind of like the first time that anyone had brought up such a thing. So this is a famous talk he gave in 1872. And it's kind of interesting because it's around this time where things about continuity and differentiability were at first being thought about. So the first person to actually talk about continuity was Bolzano, except he was in Prague. He was a Czech mathematician. He was kind of out of the. So he did all these things in the early 19th century, but no one really knew about it. And so we know Weierstrass proved his theory 50 years after Bolzano. And it wasn't until after he published, it was originally called the Weierstrass theorem. And then somebody said, oh, actually Bolzano proved this 50 years ago. So Bolzano was the first one to come up with like the epsilon delta idea of continuity. He was the first one to think about uniform continuity. So there's uniform continuity and there's pointwise continuity. And really, it wasn't until around the 1870s that uniform continuity sort of latched on as a thing. So Bolzano's ideas weren't put forward. So around this time was when they were coming up with the ideas of continuity. And everyone thought that a continuous function is basically differentiable. That if it's not differentiable, then it's only going to be at a finite number of places, or at worst, a countably infinite number of places. Like everyone assumed that. And in fact, there were lots of theorems that actually were based upon that, which were actually garbage. And of course, the thing that made it hard was back in those days, they didn't have any way of presenting these functions. They didn't have computer graphics or anything like this. So Weierstrass presented this in 1872, and it's pretty easy to see that A is between 0 and 1, so it's pretty obvious that this is continuous, right? Because you can use you can bound it by a geometric series. And so it's absolutely the partial sums are uniformly continuous. So its limit is going to be uniformly continuous. And then when you take the derivative, out comes the b to the n, of course, and now a, b is bigger than 1. And so it's pretty hopeless that this thing, although you've got to be careful, of course, because you can only differentiate series term by term if the series converges. So. But anyway, you can also from the formula to the limit. So basically you go back to first principles about what a derivative is, and I'll show you in a way in a minute how they actually show that something's not differentiable. Is basically you take a limit on a certain points that go, you find a sequence Tn that goes to your x, and such that on that sequence the difference quotient blows up. So that shows you that the limit doesn't. So this is uniformly continuous. It's better than continuous, but it's nowhere differentiable. And people weren't happy when he brought this up. So Poincaré famously says it's a monster, which is where we get, there's a whole thing there about these monster functions, all these sort of counterexamples that came up around this time. An outrage against common sense, and Hermite says it was a lamentable scourge. And so you can actually see, when you see a picture of it, you can actually see that it's a fractal, right? So that if you take a little bit of it and zoom and blow it up, it looks like the function. And in fact, that's its dimension. And that was conjectured for a long time. It actually wasn't actually proved until 2018. That actually is the fractional dimension of the fractal. So here's another approach using the Banach fixed point theorem, which I thought was pretty cute. So I thought I'd bring this in. So, so there's a function from the unit interval to the unit interval that is continuous and therefore differentiable. Okay, so if we look at the set of continuous functions from the unit interval, real value, it's a metric space under the super norm. In fact, it's a complete metric space. And so we're going to have a look at the subset of these functions, which such that f of 0 is 0, f of 1 is 1, and it maps the unit interval to the unit interval. And it's not hard to see that that is a closed subset. And so it's also a complete metric space under the sup norm. And so now we have a look at this functional. So this is something which takes a function to a new function. So what it does, so let's have a look at what it does. So let's start with just the function x. So what it does, in the first thing, so you speed it up 3 times in the x-axis, but then you shrink it down. So at the point 1/3, you go to 3/4. And go there. Then to 2/3, again you speed it up 3 times. Now you're going backwards. It's going down to 1/4. So you go down to here. And then for the last 1/3, again you speed it up 3 times. You're going from 1/4 to 1. Okay, and so you notice that no matter what f is, you're always going to these 2 points. So no matter what f is. And then if you do it a second time, right, then that's what's going to happen is you're going to take this function here, you're going to speed it up 3 times, and then again put it to there. Then you run it backwards down to there, and then you do it to there. So in the double thing, you're also going to fix what those points are, etc. So you just think of a number and you put it into base 3 fractions. Anything with a finite base 3 fraction, eventually an f hat is going to give you a value at that point. Okay. Now, the thing that's interesting about it is it's a contraction. So it's a contraction. So hat is a contraction from x to x, and it's got a Lipschitz constant of 3/4. What does that mean? So if we take so looking at the sup norm of this is, well, it's actually equal to 3/4 of the sup norm of f minus g, which is pretty easy to see, right? Because if you've got f hat minus g hat, or you've got f hat of 3x minus g hat of 3x, you look at the sup of that, and it's just going to be the sup of f minus g. Again, you're going to get the sup of f minus g here, and the sup of f minus g here. And here you're just multiplying it by 3/4. Here you're multiplying it by 1/2. Here you're multiplying by 3/4. So in the sup norm, it's shrunk the distance between f and g by 3/4. So it's a contraction, and so you've got the Barnard fixed point theorem, and it says that there exists a h with h hat equal to h. Okay, and so for free, you get it's continuous. And the only thing you've got to worry about is showing that it's nowhere differentiable. But this is the key step here, right? Because you can actually figure out what h. So these are exactly the points which have a finite expansion, finite decimal, not decimal, finite fractional expansion in base 3. So you can, so eventually, after doing the hat n times, you can actually figure out what these values are. And so by induction, you can prove this. And so what you do, like I said, so you want to show it's not differentiable at a point. So you can construct a sequence that goes to that point. And that's kind of easy because what you do, because these numbers are dense in 0, 1, right? Because any number has a base 3 decimal expansion, and you just take that limit, put that there. And so you choose this point here to be either that or that, depending upon which one maximizes the difference between the function value of the function at A and the value of the function at one of those points. Now, by our construction, the distance from Tn to A is going to be less than 1 on 3 to the n. And by the triangle inequality, the distance between h of Tn and h of A, well, we split it up into 2 bits. Remember, A is between these two bits. So if we do twice of it, it's going to be greater than 1 over 2. Because remember, we're taking the one that's got the greatest difference, h of A. And then you just put those together, and you see that the difference quotient has to be bigger than that. And that goes arbitrarily large. That's quite a nice. And basically, I think that's what they did, a similar kind of proof for the Weierstrass function. Again, you come up with a sequence that something like that. And in fact, you can do the same thing for the, we're going to do the same thing here. So again, we've got this set of continuous functions, real valued functions on the interval. It's still a complete metric space under the sup norm. And so it's a bare space now. And so the idea then, if you're doing something with bare space, you need to find open dense sets. So either you find open dense sets or you find closed sets with empty interiors. So they're the basic item. So what you want to do is we want to define an open and dense set. And the way we construct our UNs, it's going to turn out that the intersection of these sets are going to be any function that's in that intersection is going to be nowhere differentiable. Okay, so n is going to turn out to be really 1 on n. It's going to be our epsilon that we're going to use. But since it's a bare space, the space is dense in C. So we've shown that not only do they exist, but you can approximate any continuous function by a continuous nowhere differentiable function. So it's much worse than what the people in the 19th century thought. And so this is what I mean by being able to approximate. Given any continuous function, given an epsilon greater than 0, there's a continuous function which such that h minus g is less than epsilon. That's in the suit norm, so that means hx minus gx is less than epsilon for all x, and g is nowhere differentiable. So you see, the only really hard thing is defining the sets un. And that's do. Okay. So on the unit interval, so we're only interested in having our deltas be less than half. And so what you see here, these things, of course, are just slopes of secant lines. So we're going to define, okay, so we've got a function, we've got a point, and we've got how, what's our run for our secant line. And so it's either going to be this, or the maximum of those two. The reason why we've got to put this in here, right, because so for example, if delta equals a quarter, if we're between 0 and a quarter, we can only have our secants going this way. And if we're between 3/4 and 1, we can only have our secants going that way. And if we're between a quarter and a 3/4, we've got a choice of which secant line we're going to do. So example, if this is our point, so here we've got some parabola, and we've got some point close to a half. So we've got two choices for our secant lines. So we're going to take this secant line because it's the steeper. Okay, so of course, if our function is differentiable with x, this is just the difference quotient for the secant, then if we take the limit as delta goes to 0 of this, it's going to give the absolute value of the derivative if it's differentiable. So what we want to do, of course, is negate this. So we want to find an f such that given our x, we're going to find a sequence of runs that are going to go to 0, for which this becomes arbitrarily large. And this is the trick. Okay. So again, we're given our f, and we're just going to let this thing be the quantity of the infimums of all those possible secant slopes. Okay, and so we're going to start off with our u1 being all the continuous functions, but then for n greater than 2, we're going to let un be the set of the function, the continuous functions, such that there exists a delta less than 1 on n with that infimum greater than n. So these are functions whose secant lines are steep. And the way that we handle this to make use of it is we look at sawtooth functions. Now, what are we trying to do? We're trying to make our function that we're doing close to the continuous function that we're doing. So we're going to want to approximate the function by a sawtooth function because sawtooth functions are steep. Now, the trouble is, if it gets too high, then you're going to be far away from the function. but that's okay. You just put in more teeth. And so, for example, if we look at this one here, it's just one tooth, right? So here's alpha on 2. For all x, the slope of the secant line is going to be alpha, right? Because it's alpha on 2.5. Like if we're at this point here, we're going to go in this direction. If we're here, we're going to go in this direction. If we're here, we go this secant line here, and if we're in the middle, it doesn't. We're going to choose this one rather than the one that crosses onto a different line segment. So what we're going to do is we're going to make sure our delta is small enough so that we're allowed to have our secant lie on the sawtooth function. And so in this case here, G is going to be UN whenever alpha is greater than n, which is kind of going the wrong way, right? Because we want to make n big. So that means we're going to make alpha big, which means we're going to end up far away from the function. But as I said, the way we do that is we just put more teeth in. So for example, over here, here's a different sawtooth function. Again, the slope of the secant line is alpha. So now we've just got to have a smaller delta to make sure that we get our secant line here. And so again, K is going to be in UN whenever alpha is bigger than n, which is good, right? Because we've made our heights of our function smaller, so it's going to be less distance from our function. So this is the basic thing that makes everything work. Okay. So how do we do the proof? So the fact that the intersection of all of these is nowhere differentiable functions is very straightforward, right? Because since it's in anything in here is in all UNs, and so being in a particular UN for a fixed n means that we can find a delta n less than or equal to 1 on n, such that the slope of the secant line is bigger than n. Okay? So if it's in UN for all n, then we can easily come up with a sequence that satisfies that. UN is open in C, that's also pretty straightforward. The actual problem, right, is to show that UN is dense. So that's what we'll concentrate on. So what does it mean to be dense? So that means given any continuous function, any epsilon greater than 0 and our n, we need to find a function, a continuous function, which is within epsilon of f in the sup norm and is in UN. So that's what it means to be dense. And here's how we go about doing it. So notice the nice thing is because of bare spaces, instead of having to prove all at once at every point it's not differentiable, we only have to kind of show that it's not differentiable at a finite number of points, really. And so since that is true for every n, because of the bare category theorem, we get our denseness. Okay, so the first thing you do is you choose an alpha bigger than n. And then, because f is continuous on a unit interval, it's also uniform continuous. So therefore, that means we can come up with a partition of unit interval such that f varies at most epsilon on 4 on each sub-interval. And so let's say here is our here is our subinterval here. Okay, so the first thing we're going to do is we're going to construct an intermediate function g1. And so what g1 does is g1 of t is going to equal f of t at the partition points. So here, 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 and here. And then what g1 is going to do is g1 is going to be constant for a while until some point before the next partition point, we just join these points by a straight line. And we delay it till we get to a point where the slope of this line is greater than alpha. So G1, and that's straightforward to do. So G1 consists of a constant piecewise continuous function made of constant intervals, and then places where they're non-constant, they have steep slope. Have slope greater than alpha, which of course is greater than n. And of course you can always do this, right? As long as these points have different values. What happens if they have the same value? Well, you can't do that then. You just join it over by a constant line. Okay. Now, the nice thing about it is that G1 is this piecewise continuous function, and it's not very far from f. It's within epsilon 4 of f. And now we're ready to put it in our function, and so we replace every constant function with a sawtooth function, like we've seen before. And all we've got to, what we do is we add a sawtooth, and we let the height of this function be epsilon on, what's it, epsilon on 2. And so we can do that, and we can make the slope of each part of the sawtooth at least alpha. And that does it.
So what are we using to say that G exists?
Sorry?
Isn't the fact that G exists what we're trying to prove?
Yeah. So we constructed G. So G is in UN.
Okay.
So G consists of a whole bunch of little line segments, each one of which is steeper than alpha, which is steeper than n, so it's in UN. Okay, and since G1 was epsilon on 4 from f, and G is epsilon on 2 from G1, G is less than 3/4 epsilon from f. So it's within epsilon of f. And that's it. So the nice thing about the bare category theorem is we only have to prove this much. And the idea is then we can just keep on doing that. So given f, we can find a G for any n that's going to lie within epsilon and whose line segments are steep enough. So because of the denseness, we can then find there has to be a function then, because of completeness, I guess, which is kind of like a limit of all these things, which is going to be nowhere differentiable. So I don't think it's that unsatisfactory, as you know, not being defined, because basically we've shown how you turn any continuous function can be approximated by one of these functions. Is that okay?
Maybe.
So what is any?
Going back to when we were talking about the sawtooth function first. Yeah, so it's
So this,
the point is that if you give it a constant function, you can just take a sawtooth of height, whatever you want, like epsilon.
right, so exactly, so we can take alpha to be epsilon.
Right.
So this function is epsilon 2 from the zero function.
And we can just transpose that up to the constant function.
Yeah. And so this is going to have, and so the point is that so the other constraint is that you can't make it too far, right? Because then it'll but you're saved by just putting in more teeth.
That, so the point is we can do that for a partition of any size, right?
Right.
And that's what's telling you these things.
Exactly. So
Or that's what's telling you. What is telling you these things? So, oh, it's because there was an epsilon at the given.
right. So you start with a function which approximates it, and then you're approximating that with it. And then by the triangle inequality, as long as you choose your epsilons small enough, you're good. Right, because we do n here, but really the thing that we're interested in is 1 over n, because that's going to be our epsilon. It's going to be 1 over n.
That is really wide. This theorem, I mean, that's like, I don't know, I thought these things, these continuous nowhere differentiable things were few and far between, you know.
Right, but it's it's kind of like, you know,
But they're everywhere in some sense, they're dense and.
right. And it, you also like the fact that, you know, in the real numbers, transcendentals swamp.
Oh, yeah. Well, that's where all the uncountability is.
Right.
Because the unbreakable.
Right, so we've got these transcendental numbers, but we hardly know hardly any of them.
Right.
So it's the same. So these are kind of like transcendental continuous
Yeah.
functions, if you like.
Yeah.
It is kind of weird.
Do you know what kinds of theorems people were proving that said like it can, like you said about people thinking continuous functions were basically differentiable?
Right. And so I think they were proving theorems, like theorems that we would think belong to differentiable functions, but they were proving it for continuous functions.
Oh, right.
So I don't think it was a disaster.
Mhm.
But it was, but they were just assuming it. And so it's really, I mean, all this time around the 1870s is when they started focusing on this, and then out of it, I mean, this is where topology came out of that discussion. So people like Baer were, functional analysis. And they really did doing topology. And like Cantor, when he did his set theory, he was studying function. He was an analysis. And he was studying this problem of how many discontinuities, how discontinuous can something be given something. And so that led into set theory.
Yeah.
So that came as an offshoot directly of, he came up with the idea of countable and uncountable from investigating functions. So, yeah.
So what about Bolzano? He made the idea of continuity. When was that?
So he first came up with continuity like 1817. But
People, like before that, people had some, like people knew that like polynomials satisfied intermediate values, stuff like that
Right.
before that, right?
And like definitions of like Cauchy's definition of continuous was that if x changes a little bit, then the function changes stuff.
Right.
Which is like,
I mean, it's intuitive.
It's intuitive,
It's good for teaching how to work.
right, but it's hard to do anything. And so Bolzano's work was either unpublished or was published in obscure East European journals because he got into trouble. Right, so he was in Prague, I think. So he was some kind of Czech of Italian background, and he was actually a priest as well. And he taught at the university, and he got into trouble, political trouble, because he said things like, war is a bad idea, things like that. So he was kind of radical, and so he had to be, he was pushed out, and he was sent to the countryside, and said, you can't publish anything. And so all this stuff wasn't published until, he came up with uniform continuity in like the 1830s, which is well before, but nobody knew it. So uniform continuity didn't really come along until like 1870s.
So like Euler was like the late 1700s, right?
Right.
He was doing all this stuff with like infinite series and
Right.
and how was an idea of even continuity.
Well, they had, Euler used infinitesimals, so which actually doesn't get you into trouble. But that's like,
So he had some kind of idea of like at least sequential convergence.
yeah, and like pointwise convergence, but they didn't look at uniform convergence at all. And and so it wasn't until these ideas were being discussed, like I said, like Weierstrass didn't even know that Bolzano had proved that theorem 50 years earlier until he became famous for it. He said, oh, Bolzano did it 50 years earlier. So it's kind of weird. But yeah, that 1870, that's like, yeah, there's people like Dirichlet, who, define rigorously what the real numbers were as well. So,
When were Newton and Leibniz before or after 1817?
Newton and Leibniz, there, like 1600s.
Didn't they come up with like differentiation and integration without the idea of continuity?
Yeah.
That's strange.
So, but I mean, Fermat came up with derivatives before Newton and Leibniz, because they would, you do things with infinitesimals in like in the following way. So you want to find, for example, the derivative of x squared. So you do x plus epsilon squared minus x squared, right? So you get 2x epsilon plus epsilon squared. If epsilon's an infinitesimal, then you can ignore that. And then you divide through by epsilon, and you get 2x. And that's how they knew the derivative of x squared was 2x without doing any limits. They just used infinitesimals. And then they had a similar kind of thing like defining maxes and mins using it. Worked perfectly well. So, I mean, what Newton basically did was he did everything in series.
What, like power series?
Power series, yeah. He so what did he do? He found they found the power series for sine using all kind. Well, he found the power series for arc sine from sort of geometric problems like using areas and stuff like that. He then inverted the power series to get the power series for sine, and then he squared that power series and subtracted with 1, took the square root of that power series, and that's how he got the power series for cos. So he was that was